Hello everyone, welcome to this lecture. So, in this lecture we will see another protocol, another perfectly secure protocol which will be useful later for getting our pre-processing phase protocol to generate secret shared random multiplication triples. So, this protocol is for verifying multiplicative relationship among three polynomials. This protocol is called as the polyver protocol. Poly stands for polynomial and ver stands for verification, and this is a perfectly secure protocol. Later on we will see polyver protocol where there might be a negligible error involved, but this is a perfectly secure protocol where the verification happens in an absolutely error free fashion. So, what exactly is the input for this polynomial verification protocol? We will have three polynomials, an A polynomial and B polynomial and C polynomial. The degrees of A and B polynomial will be t, whereas the degree of the C polynomial will be 2t, and there will be n points on the A, B and C polynomials which will be secret shared. Okay. However, so basically what you can imagine is that you are given here n number of secret shared triples. Okay. The A components of all these secret shared triples lie on a t degree polynomial A. The B components of all these secret shared triples lie on a t degree polynomial B, and the C components of all these secret shared triples lie on a 2t degree polynomial C. The polynomial the triples, the input triples, I stress, need not be multiplication triples. So, for instance, C1 may not be equal to A1 times B1 and so on. That is the input, that is the input for this protocol, and here the relationship among t and n will be the following. T will be less than n over 3, and for simplicity we will be focusing on the case where n is exactly equal to 3t plus 1, that is the smallest value of n satisfying the condition t less than n over 3. Now, what is the goal of the protocol? What exactly is the output? The goal here is to check whether the C polynomial is the product of A and B polynomials. Now, you might be wondering what is the big deal in that. Why can't we simply reconstruct all these triples, right? Since all these triples are secret shared, we can apply the Reed-Solomon error correction algorithm. We can ask each party to make public its shares of all the triples, and then we can apply the Reed-Solomon error correction. As a result of that, all the triples will be known to the parties. Okay. And then they can check whether this property holds or not, because once they know the exact value of all these triples, they can check whether A1 times B1 is equal to C1 or not, A2 times B2 is equal to C2 or not, and then like An times Bn is equal to Cn or not. If all these equalities hold, then we can conclude that a C polynomial is indeed equal to the product of A and B polynomials. But we cannot do that, because another property which we require from the polynomial verification protocol is the following. We require that during this verification process, at most t points on the A, B and C polynomials should be revealed to the adversary, not more than t. This automatically implies that if the A, B and C polynomials were unknown to the adversary to begin with, then at the end of the protocol, adversary should learn at most t points on those polynomials. It cannot figure out what exactly was the entire A polynomial, B polynomial or C polynomial. Okay. So, that is the requirement, and because of this requirement, whatever method I suggested earlier, namely we make all these triples public and then check whether all the triples are multiplication triples, that will not work, because in that protocol the adversary end up learning more than t points on the a, b and c polynomials, because it learns all the n points on the a, b and c polynomials. So, that method will not work, right. So, instead we have to use a different approach. So, let us see the protocol here. The idea behind the protocol is as follows. What we will do is, there are n number of secret shared triples. We will designate each party to verify one of these triples. So, for instance, the ith party can be designated to verify whether the ith input triple, the ith secret shared input triple is indeed a multiplication triple or not. For that, what we have to do? We have to just let the ith secret shared triple to be reconstructed only towards the party pi. And how we can do that? Well, we can do that by asking every party to send its shares of these triples only to the party pi instead of sending it to every other party. So, only to the party pi, and then party pi can apply the Reed-Solomon error correction on the received shares of ai, bi and ci. Since we are working in the setting where n is equal to 3t plus 1 and the degree of sharing of ai, bi and ci is t, even if up to t shares for ai, bi and ci are corrupt, party pi can error correct them and it can robustly reconstruct the ai, bi and ci values. And then once it learns the ai, bi and ci values, it can verify whether this triplet ai, bi, ci constitutes a multiplication triplet or not. If it constitutes a multiplication triplet, then pi says that okay, I have checked personally, privately I have checked, and indeed this triplet ai, bi, ci is a multiplication triplet. Otherwise, pi makes public an NOK message. So, this OK or NOK message is broadcasted. By broadcast, I mean a reliable broadcast protocol is used here by pi to make public the OK or the NOK message. Notice that if pi is honest, then only if the triplet is not a multiplication triplet, it will broadcast an NOK message. However, if pi is corrupt, then even though the triplet ai, bi, ci is a multiplication triplet, it may unnecessarily broadcast an NOK message. So, we do not know whether party pi is honest or corrupt. Okay. If it is honest, then indeed it will perform its steps properly. That is, it will broadcast OK only if the triplet is a multiplication triplet, else it will broadcast an NOK message. So, now what we have to do is, if pi broadcasts an NOK message, then we do not know whether pi is lying or whether pi is behaving honestly. That means, whether we should consider the complaint of pi genuine or not. If it has made a complaint by making public an NOK message, then that is a complaint. That means, it is complaining against the ith triplet, and to verify whether its complaint is indeed genuine or not, what we do next is that we now publicly reconstruct the ith triplet. So, you see this public reconstruction of the ith triplet is optional. It is happening only when a complaint is made against the ith triplet by pi, and only pi can complain against the ith triplet. That means, the first triplet P1 is designated to check, the second triplet P2 is designated to check, the ith triplet ith party is designated to check, and nth triplet the nth party is designated to check. Now, the designated verifier here, what they are doing is, they are either making public an OK message or an OK message. If one of the designated verifier has made if any designated verifier has made public an NOK message for its triplet, that means now it is the time to check it publicly. because we cannot trust the designated verifier. The designated verifier could be corrupt and it might unnecessarily complain against the ith triplet even though it is a multiplication triplet. So, that is why now it is time to publicly check it, and this step is optional. That means, if PI has broadcasted an OK message for the ith designated triplet, then it is fine, no need to check it, we trust PI. But if a complaint is made, fine, it is a time to publicly check it, and to publicly check it, the value AI, BI, CI needs to be publicly reconstructed. So, that is why in this picture I am showing this AI, BI, CI now in clear, that means it will be learnt by everyone. How this AI, BI, CI will be publicly reconstructed? Well, every party will be asked to send its shares of AI, BI and CI to every other party, because it is now a public reconstruction, and then every party will apply the Reed-Solomon error correction algorithm and they will reconstruct the value of AI, BI and CI. Now, once this triplet is available publicly, PI's complaint will be called, it will be termed genuine if indeed this triplet turns out not to be a multiplication triplet. Okay, this turns out to be a non-multiplication triplet, that means CI is not the product of AI and BI, then we will consider PI's complaint to be genuine, otherwise we will label the PI's complaint as fraud complaint. Okay. Now, what is the output of the protocol? The output of the protocol is success if and only if there are no genuine complaints against, if and only if there are no genuine complaints. That means, either every party has broadcasted an OK message, or wherever there are NOK messages which are broadcasted, those complaints turned out to be non-genuine. If this is the case, then the output of the protocol is success, that means the C polynomial is indeed the product of A and B polynomial, otherwise the output is failure. That is the polynomial verification protocol, right. So, these are the steps of the protocol. Now, we have to prove what are the properties achieved by the protocol. The crucial property we wanted is that if the C polynomial is not equal to the product of A and B polynomial, then the output should not be success. So, we are going to prove that. So, we first prove that if indeed the C polynomial is product of A and B polynomials, then all honest parties will output success. Why honest parties? Because we do not care what the corrupt party's output. That means, even though a corrupt party should output success because all the complaints are non-genuine, it may still end up outputting failure. We cannot prevent corrupt parties from doing that. But what we want here is that if the C polynomial is indeed the product of A and B polynomials, then all honest parties should output success. Let us see whether that is happening here or not. So, if the C polynomial is the product of A and B polynomial, what exactly every honest party PI is going to do? So, party PI is designated with the task of verifying the ith output triple. So, I am considering here an arbitrary honest PI. That arbitrary honest PI would have learnt the value of AI, BI and CI. And what exactly AI, BI and CI? AI is equal to the A polynomial at alpha I. What is the BI? BI is the value of the B polynomial at alpha I. And what is CI? CI is the C polynomial at alpha I. What is the hypothesis of the claim? The hypothesis of the claim is that the C polynomial is the product of A and B polynomial. If C polynomial is the product of A and B polynomial, that means the C polynomial at alpha I is equal to A polynomial at alpha I times B polynomial at alpha I. A polynomial at alpha I is Ci, the ith component, the C component of the ith triple. Sorry, what is C of alpha I? C of alpha I is the C component of the ith triple. What is A of alpha I? It is the A component of the ith triple, and what is Bi? It is the B component of the ith triple. So, since party Pi is honest and it learns Ci, Ai, Bi and Ci is the product of Ai, Bi, it will find that Ai, Bi, Ci is a multiplication triplet, and as a result of that it will broadcast OK message. However, if Pi is corrupt, it may broadcast an NOK message. That is quite possible, even though the triplet is a multiplication triplet. But then if it broadcasts an NOK message, then the triplet will be publicly reconstructed, and after publicly reconstructing it, everyone will find that okay, Pi's complaint is not genuine, because it has simply complained even though the triplet Ai, Bi, Ci is a multiplication triplet. So, it will not be considered as a genuine complaint, and as a result of that everyone will output success here. On the other hand, suppose the C polynomial is not the product of A and B polynomial, then we claim that no honest party outputs success. Again, why an honest party? Because in this case corrupt parties may simply end up outputting success, even though the C polynomial is not the product of A and B polynomials. So, for proving this claim, let us focus on the set of honest parties. I denote it by this fancy H, and for simplicity imagine that the first 2t plus 1 parties are honest. Why 2t plus 1? Because we are considering a setting where n is equal to 3t plus 1. There could be up to t corrupt parties. So, we take the worst case when there are exactly t corrupt parties. That means we are left with exactly 2t plus 1 honest parties. They could be any 2t plus 1 honest parties, but for simplicity let me take those honest parties to be the first 2t plus 1 honest parties. So, what is the hypothesis of the claim here? Claim statement that the C polynomial is not the product of A and B polynomials. If that is the case, then the claim here is that there will be at least some honest party Pi corresponding to which the value of the C polynomial at alpha I will not be equal to the value of the A polynomial at alpha I times the value of the B polynomial at alpha I. This is because if this is not the case, that means if there is no such honest Pi, that means the C polynomial at alpha 1 is equal to A polynomial at alpha 1 times B polynomial at alpha 1, and corresponding to P2 the C polynomial at alpha 2 is equal to A polynomial at alpha 2 times B polynomial at alpha 2, and like that say the C polynomial at alpha 2t plus 1 is equal to the A polynomial at alpha of 2t plus 1 times the B polynomial at alpha of 2t plus 1. Then together this implies that the C polynomial is equal to the product of the A and B polynomials, which is a contradiction. How we get C polynomial equal to A polynomial times B polynomial? Because this equality holds for 2t plus 1 distinct points. The degree of the C polynomial is 2t and the degree of the A and B polynomials is t, and if this equality hold, then the C polynomial will be equal to A polynomial times B polynomial, which is a contradiction, because as per the hypothesis of the claim statement, the C polynomial is not equal to the product of A and B polynomials. That means there is definitely at least one honest party Pi in the system corresponding to which the value of the C polynomial at alpha I is not equal to the value of the A polynomial at alpha I times the value of the B polynomial at alpha I. That is guaranteed. It could be any Pi in the set H. It could be either P1 or P2 or P3 or Pi or P of 2t plus 1, we do not know, but the existence of such a Pi is guaranteed. Now, if that is the case, then it automatically implies that the ith triplet here, the ith secret shared triplet is not a multiplication triplet, because all these triplets constitute distinct points on the A, B and C polynomials. Now, what exactly that honest party pi would have done in the protocol? When the party pi would learn the ith triplet, when it is reconstructed towards the party pi, it will find that it is not a multiplication triplet and hence it will publicly complain, it will broadcast an NOK message. And as soon as it broadcasts an NOK message, it will be publicly reconstructed. No one will prevent, the adversary cannot prevent the reconstruction of this triplet robustly. That means, it cannot provide incorrect shares and hope that the triplet is reconstructed incorrectly. So, whatever is the value of the triplet, it will be reconstructed correctly, because everyone will be applying the Reed-Solomon error correction algorithm. And as soon as this triplet is publicly learned, it will be known to everyone that it is not a multiplication triplet. Hence, PI's complaint will be considered as a genuine complaint, and as a result of that, no one will output success. Now, let us prove the last property. We claim here that if the C polynomial is equal to the product of A and B polynomials, in fact, irrespective of whether the C polynomial is equal to the, the claim statement is if the C polynomial is the product of A and B polynomials, then throughout the protocol, adversary learns at most t points on these polynomials. That is the claim here. So, let C be the set of corrupt parties in the system, and again we take the worst case when there are exactly t corrupt parties in C. So, what exactly the adversary learns here? In the protocol, every party is designated to first privately check one of the n secret shared triplets. So, since there are t corrupt parties, that means there are t corresponding designated corrupt verifiers who will be verifying up to t number of secret shared triplets here. That means, they will be learning the value of A polynomial, B polynomial and C polynomial at alpha I corresponding to every corrupt pi, and there are at most t such, in fact, there are exactly t such corrupt parties, because we are assuming that there are t corrupt parties in the system. So, that is one case, and now corresponding to every honest party, adversary does not learn anything about the corresponding input triplet. So, if pi is not a corrupt party, that means, if pi is an honest party, since C polynomial is the product of A and B polynomial, it will broadcast an OK message instead of an OK message, and no one will be publicly reconstructing the ith input triplet. That means, this ith input triplet will not be publicly reconstructed, it will be reconstructed only by pi, and since pi is assumed to be honest, that means, adversary does not learn what exactly is the ith input triplet. So, that means that if the C polynomial is the product of A and B polynomials, adversary can learn at most t of these n number of secret shared triplets during the polynomial verification protocol. So, you can see now that we have achieved all the protocols, and you can see that why this protocol is perfectly secure. This protocol is perfectly secure because all the properties are achieved against the computationally unbounded adversary, and there is no error associated with any of the achieved properties. So, with that I end this lecture. Again, the reference for this lecture is this IEEE transaction paper. Thank you.